Good morning, everybody. Today we're going to be discussing our next gas law, which is the ideal gas law. Ideal gas law incorporates the same concepts of the relationships between pressure, volume, and temperature, but now incorporates the number of particles. So if we think about this logically, the more particles you have, the more pressure they're going to exert on the vessel that's holding that gas. Similarly, if you keep the pressure constant, more particles equals more pressure, more temperature, or if you vary the volume, the more particles will increase the amount of volume. So it's the same concept. We still get that same relationship. Matter of fact, it's a direct proportion for that. So the ideal gas law is basically an ideal gas is a hypothetical gas whose molecules occupy a negligible space and have interactions with each other, and they basically obey the gas laws exactly. So it comes up with a formula that's PV equals nRT, one of my favorite formulas in chemistry. So in this case, P is pressure, and that could be in atmospheres, kilopascals, torrs, all the same ones we've talked about. Volumes should be in liters, not milliliters. And N in this case is number of moles of gas. That's going to be important. Remember, we always measure everything in moles. R is a gas constant. We'll get to that in a bit. And its number varies based on the pressure being used in the calculation. And finally, temperature is always in Kelvin. We want to have absolute temperatures. The ideal gas constant has different value based on the pressure being used. So the value of R when the pressure is in atmospheres is 0.0821 liters atmospheres divided by mole Kelvin. When we go to kilopascals, it's 8.31 liter kilopascals mole Kelvin, and torr is 62.4 liters torr over mole Kelvin. So it's very important as you're setting up your equation that you are aware of what pressure you're using, so you know which R value you're going to put into your calculation. So ideal gas law, and we'll get into some calculations in a minute, but ideal gas law also can be used to calculate density and molar mass, and I'll show you how to set this up, or how this is calculated in a second, but we can convert it to calculate density or molar mass of a gas. So in this case, I've changed it a little bit. So we have molar mass, M, where molar mass is the M. So M times pressure, molar mass times pressure equals the density times the ideal gas constant times temperature. So how do we, just so you know, I have put all this whole thing is also here on our gas law organizer found on Schoology. So the idea gas law relates pressure, temperature, volume, and mass of a gas through R constants. So PV equals nRT. And if you ever forget what R equals, it's right down here in gas law equation symbols. R equals 8.31 liters kilopascals, 0.0821 liter atmospheres, or 62.4 liter torrs. Remember, you have to have a common set of units in the problem. So let's look at some practice. All right, so how does, actually I'll do this one second. So let's go over here and look at how many moles of oxygen will occupy a volume of 2.5 liters at 25 degrees Celsius and 1.2 atmospheres. There we go, now I can see everything. All right, so we have our formula, PV equals nRT. I'll put this in black. So let's just go ahead and I'm going to set up my variable box. P is, oops. Oh, look at that, being messy already this morning. P in this case is 1.2 atmospheres. Volume is 2.5 liters. We're looking for N. We don't know what that is. R in this case is, since we are looking at atmospheres here, we're going to use 0.821. So 0.0821 liters atmospheres over mole Kelvin. And then temperature is 25 degrees Celsius, but we want that in Kelvin, so let's go ahead and multiply or add 273 to get 298, right, Kelvin. So we can plug everything in. If I simplify this, N is going to be PV over RT. So N equals 1.2 atmospheres times 2.5 liters over 0.0821 liters atmospheres mole Kelvin times 298 Kelvin. So we can see here, atmospheres is going to cancel here, liters is canceling, Kelvin is going to cancel, leaving us with moles on the bottom, which of course any denominator within a denominator moves this right up to the top. So in this case we have N equals 0.1226 moles. And since we are dealing with 2 sig figs as our smallest, so N equals 0.12 moles. All right, simple enough calculation. Let's look here at, we looked at it a little differently. What volume will 2.0 moles of nitrogen occupy at 720 torr and 20 degrees Celsius? I'm just going to go ahead and grab this and bring it all the way over, sorry for the mess, over here so we can see our R value. All right, so we have pressure is 720 torr. Volume is our unknown in this case. N equals 2.0 moles of nitrogen. R, in this case, since we are looking at torr, we want to use this one, 62.4 liters torr moles Kelvin. And temperature is 20 degrees Celsius plus 273 gives us 293 Kelvin. So in this case, volume, if I take PV equals nRT, if I isolate volume, we're going to have N, volume is nRT over P. So we have 2.0 mole times 62.4 liters torr mole Kelvin times 293, okay, over 720 torr. Our volume in this case, we do put that in the calculator, it's going to plug out to 50.78 liters, and since we have 112 is our smallest sig figs, we're going to have a final of 51 liters. All right, so those are the simple ones to talk about initially. So now let's look at how we can convert density, or the ideal gas law, into an equation that takes into account density. All right, so if we're starting with PV equals nRT, there's a few things we need to understand. All right, density is grams over liters, which is basically mass over volume. And remember, molar mass equals grams over moles, which is mass over moles. So if we think about, if we start by solving for volume, so we have volume equals nRT over P, that we can now isolate that. And if we think about this, we have our density is mass over volume. If we convert this, and if we convert volume into density, we can basically take everything and have mass over that. So we have mass over volume, that's our density. Now we have mass over nRT over P, and since P is a denominator within a denominator, we're going to move that right to the top. So we end up here with mass, little m, times pressure over number of moles RT. Okay, so we've already solved for D. We now have density equals mass times pressure over nRT. If we think about, remember, N is moles, and if we have molar mass is grams or mass over moles, M over N, we have molar mass there. So density equals molar mass, I'll call that a big M, P over RT, or in this case, we multiply both sides now by RT, we get density times ideal gas constant temperature equals molar mass times pressure. So we can use this to calculate densities. If you know what the molar mass is, you're going to use this. You'll use this formula. If you don't, if you know number of moles, or you know the mass of something, or you know the density and you need to know the mass, you can use this one. But either way, the basic is we have this more simplified version of the ideal gas law using density and molar mass. So let's do an example problem. Oops, scoot way over here. And I'm just going to quickly erase this so we can get an idea what we're working with. And I'll grab this and pull it over so we can see better. All right, so I have CO2 gas is exerting 77.8 kilopascals pressure at 300 Kelvin. What is its density? So if we think about this, we have pressure and we have temperature. We don't have anything else, or do we? If we know we have CO2, we can calculate the molar mass of that. And so if we think about that, we have a pressure is equal to 77.8 kPa. We're not worrying about volume. We're going to be looking at this formula down here. So molar mass, in this case, is the molar mass of CO2. So if we look at our periodic table, we have 12 plus 16 times 2 gives me 44 grams per mole. We have our R value. In this case, since we are using kilopascals, we want to use the R value over here of 8.31. So we have 8.31 liters kPa, terrible kPa, times moles Kelvin. And our temperature density, again, is our unknown. Temperature in this case is 311 Kelvin. So seeing that, we can now plug this in. So density, if we solve for density, mass times molar mass times pressure equals density RT right here. We solve for density, we can get that as molar mass times pressure over RT. So we have 44 grams per mole times 77.8 kilopascals over our R value is 8.31 liters kPa mole Kelvin, and 311 Kelvin. Double check our work by doing all the canceling out. So we can see our kelvins are going to cancel out. Our moles over here are going to cancel out. Kilopascals cancel out, leaving us with grams over liters. It should not be a capital D. It should be a little d. Fix that. So just going to bug me if I don't. So if we do the calculations, we end up with 1.32 grams per liter. That's what we're left with our units. Always double check your units so that you know how that you are doing that. You're setting up the equation right. And so that's the answers you should get. All right, so that's enough. We're showing some modeling. I have an assignment for you with a number of practice problems. Please do those, submit them online. And if you have any questions, send me an email. If you want to do some face-to-face work, again, I'm available during office hours. Thanks so much, and I will talk to you soon.